Section 13 of The Outline of Science, Volume 1. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information, or to volunteer, please visit LibriVox.org. Recording by Jude Cater. The Outline of Science, Volume 1, by J. Arthur Thomson. Section 13. Part 8. Foundations of the Universe. The World of Atoms. Most people have heard of the Oriental race which puzzled over the foundations of the universe and decided that it must be supported on the back of a giant elephant. But the elephant? They put it on the back of a monstrous tortoise, and there they let the matter end. If every animal in nature had been called upon, they would have been no nearer a foundation. Most ancient peoples, indeed, made no effort to find a foundation. The universe was a very compact little structure, mainly composed of the earth and the great canopy over the earth, which they call the sky. They left it, as a whole, floating in nothing. And in this the ancients were wiser than they knew. Things do not fall down unless they are pulled down by that mysterious force which we call gravitation. The earth, it is true, is pulled by the sun, and would fall into it, but the earth escapes this fiery fate by circulating at great speed round the sun. The stars pull each other, but it has already been explained that they meet this by traveling rapidly in gigantic orbits. Yet we do, in a new sense of the word, need foundations of the universe. Our mind craves for some explanation of the matter out of which the universe is made. For this explanation, we turn to modern physics and chemistry. Both these sciences study, under different aspects, matter and energy, and between them they have put together a conception of the fundamental nature of things, which marks an epoch in the history of human thought. 1. The bricks of the cosmos. More than 2,000 years ago, the first men of science, the Greeks of the cities of Asia Minor, speculated on the nature of matter. You can grind a piece of stone into dust. You can divide a spoonful of water into as many drops as you like. Apparently, you can go on dividing as long as you have got apparatus fine enough for the work. But there must be a limit, these Greeks said, and so they supposed that all matter was ultimately composed of minute particles which were indivisible. That is the meaning of the Greek word, atom. Like so many other ideas of these brilliant early Greek thinkers, the atom was a sound conception. We know today that matter is composed of atoms, but science was then so young that the way in which the Greeks applied the idea was not very profound. A liquid or a gas, they said, consisted of round, smooth atoms which would not cling together. Then there were atoms with rough surfaces, hooky surfaces, and these stuck together and formed solids. The atoms of iron or marble, for instance, were so very hooky that, once they got together, a strong man could not tear them apart. The Greeks thought that the explanation of the universe was that an infinite number of these atoms had been moving and mixing in an infinite space during an infinite time, and had at last hit by chance on the particular combination, which is our universe. This was too simple and superficial. The idea of atoms was cast aside, only to be advanced again in various ways. It was the famous Manchester chemist, John Dalton, who restored it in the early years of the 19th century. He first definitely formulated the atomic theory as a scientific hypothesis. The whole physical and chemical science of that century was now based upon the atom, and it is quite a mistake to suppose that recent discoveries have discredited atomism. An atom is the smallest particle of a chemical element. No one has ever seen an atom. Even the wonderful new microscope which has just been invented cannot possibly show us particles of matter which are 1,000,000 times smaller than the breadth of a hair, for that is the size of atoms. We can weigh them and measure them, though they are invisible, and we know that all matter is composed of them. It is a new discovery that atoms are not indivisible. They consist themselves of still smaller particles, as we shall see, but the atoms exist all the same, and we may still say that they are the bricks of which the material universe is built. But if we had some magical glass by means of which we could see into the structure of material things, we should not see the atoms put evenly together as bricks are in a wall. As a rule, two or more atoms first come together to form a larger particle, which we call a molecule. Single atoms do not, as a rule, exist apart from other atoms. If a molecule is broken up, the individual atoms seek to unite with other atoms of another kind, or amongst themselves. For example, 3 atoms of oxygen form what we call ozone. 2 atoms of hydrogen uniting with 1 atom of oxygen form water. It is molecules that form the mass of matter. A molecule, as it has been expressed, is a little building of which atoms are the bricks. In this way we get a useful first view of the material things we handle. In a liquid, the molecules of the liquid cling together loosely. They remain together as a body, but they roll over and away from each other. There is a cohesion between them, but it is less powerful than in a solid. Put some water in a kettle over the lighted gas, and presently the tiny molecules of water will rush through the spout in a cloud of steam and scatter over the kitchen. The heat has broken their bond of association and turned the water into something like a gas, though we know that the particles will come together again, as they cool, and form once more drops of water. In a gas, the molecules have full individual liberty. They are in a state of violent movement, and they form no union with each other. If we want to force them to enter into the loose sort of association which molecules have in a liquid, we have to slow down their individual movements by applying severe cold. That is how a modern man of science liquefies gases. No power that we have will liquefy air at its ordinary temperature. In very severe cold, on the other hand, the air will spontaneously become liquid. Some day, when the fires of the sun have sunk very low, the temperature of the earth will be less than -200°C. That is to say, more than 200°C below freezing point. It will sink to the temperature of the moon. Our atmosphere will then be an ocean of liquid air 35 feet deep, lying upon the solidly frozen masses of our water oceans. In a solid, the molecules cling firmly to each other. We need a force equal to 25 tons to tear asunder the molecules in a bar of iron an inch thick. Yet the structure is not solid in the popular sense of the word. If you put a piece of solid gold in a little pool of mercury, the gold will take in the mercury between its molecules as if it were porous like a sponge. The hardest solid is more like a lattice work than what we mean by solid, though the molecules are not fixed like the bars of a lattice work, but are in violent motion. They vibrate about equilibrium positions. If we could see right into the heart of a bit of the hardest steel, we should see billions of separate molecules at some distance from each other, all moving rapidly to and fro. This molecular movement can, in a measure, be made visible. It was noticed by a microscopist named Brown that, in a solution containing very fine suspended particles, the particles were in constant movement. Under a powerful microscope, these particles are seen to be violently agitated. They are each independently darting hither and thither, somewhat like a lot of billiard balls on a billiard table, colliding and bounding about in all directions. Thousands of times a second these encounters occur, and this lively commotion is always going on. This incessant colliding of one molecule with another is the normal condition of affairs. Not one of them is at rest. The reason for this has been worked out, and it is now known that these particles move about because they are being incessantly bombarded by molecules of the liquid. The molecules cannot, of course, be seen, but the fact of their incessant movement is revealed to the eye by the behavior of the visible suspended particles. This incessant movement in the world of molecules is called the Brownian movement, and is a striking proof of the reality of molecular motions. 2. The wonder world of atoms. The exploration of this wonder world of atoms and molecules by the physicists and chemists of today is one of the most impressive triumphs of modern science. Quite apart from radium and electrons and other sensational discoveries of recent years, the study of ordinary matter is hardly inferior, either in interest or audacity, to the work of the astronomer. And there is the same foundation in both cases: marvelous apparatus, and trains of mathematical reasoning that would have astonished Euclid or Archimedes. Extraordinary, therefore, as are some of the facts and figures we are now going to give in connection with the minuteness of atoms and molecules, let us bear in mind that we owe them to the most solid and severe processes of human thought. Yet the principle can, in most cases, be made so clear that the reader will not be asked to take much on trust. It is, for instance, a matter of common knowledge that gold is soft enough to be beaten into gold leaf. It is a matter of common sense, one hopes, that if you beat a measured cube of gold into a leaf 6 inches square, the mathematician can tell the thickness of that leaf without measuring it. As a matter of fact, a single grain of gold has been beaten into a leaf 75 inches square. Now the mathematician can easily find that when a single grain of gold is beaten out to that size, the leaf must be 1/367,000th of an inch thick, or about 1,000 times thinner than the paper on which these words are printed. Yet the leaf must be several molecules thick. The finest gold leaf is, in fact, too thick for our purpose, and we turn with a new interest to that toy of our boyhood, the soap bubble. If you carefully examine one of these delicate films of soapy water, you notice certain dark spots or patches on them. These are their thinnest parts, and by two quite independent methods, one using electricity and the other light, we have found that at these spots the bubble is less than the 3/1,000,000th of an inch thick. But the molecules in the film cling together so firmly that they must be at least 20 or 30 deep in the thinnest part. A molecule, therefore, must be far less than the 3/1,000,000th of an inch thick. We found next that a film of oil on the surface of water may be even thinner than a soap bubble. Professor Perrin, the great French authority on atoms, got films of oil down to the 50/1,000,000th of an inch in thickness. He poured a measured drop of oil upon water. Then he found the exact limits of the area of the oil sheet by blowing upon the water a fine powder which spread to the edge of the film and clearly outlined it. The rest is safe and simple calculation, as in the case of a beaten grain of gold. Now this film of oil must be at least 2 molecules deep, so a single molecule of oil is considerably less than 100/1,000,000th of an inch in diameter. Innumerable methods have been tried, and the result is always the same. A single grain of indigo, for instance, will color a ton of water. This obviously means that the grain contains billions of molecules which spread through the water. A grain of musk will scent a room, pour molecules into every part of it, for several years, yet not lose 1/1,000,000th of its mass in a year. There are hundreds of ways of showing the minuteness of the ultimate particles of matter, and some of these enable us to give definite figures. On a careful comparison of the best methods, we can say that the average molecule of matter is less than the 1/125,000,000th of an inch in diameter. In a single cubic centimeter of air, a globule about the size of a small marble, there are 30 million trillion molecules. And since the molecule is, as we saw, a group or cluster of atoms, the atom itself is smaller. Atoms, for reasons which we shall see later, differ very greatly from each other in size and weight. It is enough to say that some of them are so small that it would take 400 million of them in a line to cover an inch of space, and that it takes at least a quintillion atoms of gold to weigh a single gram. 5 million atoms of helium could be placed in a line across the diameter of a full stop. The energy of atoms. And this is only the beginning of the wonders that were done with ordinary matter, quite apart from radium and its revelations, to which we will come presently. Most people have heard of atomic energy and the extraordinary things that might be accomplished if we could harness this energy and turn it to human use. A deeper and more wonderful source of this energy has been discovered in the last 20 years, but it is well to realize that the atoms themselves have stupendous energy. The atoms of matter are vibrating or gyrating with extraordinary vigor. The piece of cold iron you hold in your hand, the bit of brick you pick up, or the penny you take from your pocket, is a colossal reservoir of energy, since it consists of trillions of moving atoms. To realize the total energy, of course, we should have to witness a transformation such as we do in atoms of radioactive elements, about which we shall have something to say presently. If we put a grain of indigo in a glass of water, or a grain of musk in a perfectly still room, we soon realize that molecules travel. Similarly, the fact that gases spread until they fill every empty available space shows definitely that they consist of small particles traveling at great speed. The physicist brings his refined methods to bear on these things, and he measures the energy and velocity of these infinitely minute molecules. He tells us that molecules of oxygen, at the temperature of melting ice, travel at the rate of about 500 yards a second, more than a quarter of a mile a second. Molecules of hydrogen travel at 4 times that speed, or 3 times the speed with which a bullet leaves a rifle. Each molecule of air, which seems so still in the house on a summer's day, is really traveling faster than a rifle bullet does at the beginning of its journey. It collides with another molecule every 20,000th of an inch of its journey. It is turned from its course 5 billion times in every second by collisions. If we could stop the molecules of hydrogen gas and utilize their energy, as we utilize the energy of steam or the energy of water at Niagara, we should find enough in every gram of gas, about 2/1000th of a pound, to raise 1/3 of a ton to a height of 40 inches. I have used for comparison the speed of a rifle bullet, and in an earlier generation people would have thought it impossible even to estimate this. It is, of course, easy. We put 2 screens in the path of the bullet, one near the rifle and the other some distance away. We connect them electrically and use a fine time-recording machine, and the bullet itself registers the time it takes to travel from the first to the second screen. Now this is a very simple and superficial work in comparison with the system of exact and minute measurements which the physicist and chemist use. In one of his interesting works, Mr. Charles R. Gibson gives a photograph of 2 exactly equal pieces of paper in the opposite pans of a fine balance. A single word has been written in pencil on one of these papers, and that little scraping of lead has enough to bring down the scale. The spectroscope will detect a quantity of matter 4 million times smaller than even this, and the electroscope is 1,000,000 times still more sensitive than the spectroscope. We have a heat measuring instrument, the bolometer, which makes the best thermometer seem early Victorian. It records the millionth of a degree of temperature. It is such instruments multiplied by the score which enable us to do the fine work recorded in these pages. 3. The discovery of X-rays and radium. The discovery of Sir William Crookes. But these wonders of the atom are only a prelude to the more romantic and far-reaching discoveries of the new physics, the wonders of the electron. Another, and the most important phase of our exploration of the material universe opened with the discovery of radium in 1898. In the discovery of radioactive elements, a new property of matter was discovered. What followed on the discovery of radium and of the X-rays, we shall see. As Sir Ernest Rutherford, one of our greatest authorities, recently said, the new physics has dissipated the last doubt about the reality of atoms and molecules. The closer examination of matter which we have been able to make shows positively that it is composed of atoms. But we must not take the word now in its original Greek meaning, an indivisible thing. The atoms are not indivisible. They can be broken up. They are composed of still smaller particles. The discovery that the atom was composed of smaller particles was the welcome realization of a dream that had haunted the imagination of the 19th century. Chemists said that there were about 80 different kinds of atoms, different kinds of matter, but no one was satisfied with the multiplicity. Science is always aiming at simplicity and unity. It may be that science has now taken a long step in the direction of explaining the fundamental unity of all matter. The chemist was unable to break up these elements into something simpler, so he called their atoms indivisible in that sense. But one man of science after another expressed the hope that he would yet discover some fundamental matter of which the various atoms were composed. One primordial substance from which all the varying forms of matter have been evolved or built up. Prout suggested this at the very beginning of the century, when atoms were rediscovered by Dalton. Father Secchi, the famous Jesuit astronomer, said that all the atoms were probably evolved from ether, and this was a very favored speculation. Sir William Crookes talked of prothal as the fundamental substance. Others thought hydrogen was the stuff out of which all the other atoms were composed. The work which finally resulted in the discovery of radium began with some beautiful experiments of Professor, later Sir William Crookes, in the 80s. It had been noticed in 1869 that a strange coloring was caused when an electric charge was sent through a vacuum tube. The walls of the glass tube began to glow with a greenish phosphorescence. A vacuum tube is one from which nearly all the air has been pumped, although we can never completely empty the tube. Crookes used such ingenious methods that he reduced the gas in his tubes until it was 20 million times thinner than the atmosphere. He then sent an electrical discharge through, and got very remarkable results. The negative pole of the electric current, the cathode, gave off rays which faintly lit the molecules of the thin gas in the tube, and caused a pretty fluorescence on the glass walls of the tube. What were these rays? Crookes at first thought they corresponded to a new or fourth state of matter. Hitherto we had only been familiar with matter in the three conditions of solid, liquid, and gaseous. Now Crookes really had the great secret under his eyes. But about 20 years elapsed before the true nature of these rays was finally and independently established by various experiments. The experiments proved that the rays consisted of a stream of negatively charged particles traveling with enormous velocities from 10,000 to 100,000 miles a second. In addition, it was found that the mass of each particle was exceedingly small, about 1/1800th of the mass of a hydrogen atom, the lightest atom known to science. These particles, or electrons as they are now called, were being liberated from the atom. The atoms of matter were breaking down in Crookes' tubes. At that time, however, it was premature to think of such a thing, and Crookes preferred to say that the particles of the gas were electrified and hurled against the walls of the tube. He said that it was ordinary matter in a new state, radiant matter. Another distinguished man of science, Leonard, found that, when he fitted a plate of aluminum in the glass wall of the tube, The mysterious rays passed through this as if it were a window. They must be waves in the ether, he said. 4. The discovery of X-rays. So the story went on from year to year. We shall see in a moment to what it led. Meanwhile, the next great step was when, in 1895, Röntgen discovered the X-rays, which are now known to everybody. He was following up the work of Leonard, and one day he covered a Crookes tube with some black stuff. To his astonishment, a prepared chemical screen which was near the tube began to glow. The rays had gone through the black stuff, and on further experiment he found that they would go through stone, living flesh, and all sorts of opaque substances. In a short time the world was astonished to learn that we could photograph the skeleton in a living man's body, locate a penny in the interior of a child that had swallowed one, or take an impression of a coin through a slab of stone. And what are these X-rays? They are not a form of matter. They are not material particles. X-rays were found to be a new variety of light with a remarkable power of penetration. We have seen what the spectroscope reveals about the varying nature of light wavelengths. Light waves are set up by vibrations in ether, and as we shall see, these ether disturbances are all of the same kind. They only differ as regards wavelengths. The X-rays which Röntgen discovered, then, are light, but a variety of light previously unknown to us. They are ether waves of very short length. X-rays have proved of great value in many directions, as all the world knows, but that we need not discuss at this point. Let us see what followed Röntgen's discovery. Footnote: we refer throughout to the ether because, although modern theories dispense largely with this conception, the theories of physics are so inextricably interwoven with it that it is necessary, in an elementary exposition, to assume its existence. The modern view will be explained later in the article on Einstein's theory. End footnote. While the world wondered at these marvels, the men of science were eagerly following up the new clue to the mystery of matter which was exercising the mind of Crookes and other investigators. In 1896, Becquerel brought us to the threshold of the great discovery. Certain substances are phosphorescent. They become luminous after they have been exposed to sunlight for some time, and Becquerel was trying to find if any of these substances give rise to X-rays. One day he chose a salt of the metal uranium. He was going to see if, after exposing it to sunlight, he could photograph a cross with it through an opaque substance. He wrapped it up and laid it aside to wait for the sun, but he found the uranium salt did not wait for the sun. Some strong radiation from it went through the opaque covering and made an impression of the cross upon the plate underneath. Light, or darkness, was immaterial. The mysterious rays streamed night and day from the salt. This was something new. Here was a substance which appeared to be producing X-rays. The rays emitted by uranium would penetrate the same opaque substances as the X-rays discovered by Röntgen. Discovery of radium. Now, at the same time as many other investigators, Professor Curie and his Polish wife took up the search. They decided to find out whether the emission came from the uranium itself or from something associated with it, and for this purpose they made a chemical analysis of great quantities of minerals. They found a certain kind of pitchblende which was very active, and they analyzed tons of it, concentrating always on the radiant element in it. After a time, as they successively worked out the non-radiant matter, the stuff began to glow. In the end, they extracted from 8 tons of pitchblende about half a teaspoonful of something that was 1,000,000 times more radiant than uranium. There was only one name for it: radium. That was the starting point of the new development of physics and chemistry. From every laboratory in the world came a cry for radium salts, as pure radium was too precious, and hundreds of brilliant workers fastened on the new element. The inquiry was broadened, and as year followed year, one substance after another was found to possess the power of emitting rays, that is, to be radioactive. We know today that nearly every form of matter can be stimulated to radioactivity, which, as we shall see, means that its atoms break up into smaller and wonderfully energetic particles which we call electrons. This discovery of electrons has brought about a complete change in our ideas in many directions. So instead of atoms being indivisible, they are actually dividing themselves spontaneously and giving off throughout the universe tiny fragments of their substance. We shall explain presently what was later discovered about the electron. Meanwhile, we can say that every glowing metal is pouring out a stream of these electrons. Every arc lamp is discharging them. Every clap of thunder means a shower of them. Every star is flooding space with them. We are witnessing the spontaneous breaking up of atoms, atoms which had been thought to be indivisible. The sun not only pours out streams of electrons from its own atoms, but the ultraviolet light which it sends to the earth is one of the most powerful agencies for releasing electrons from the surface atoms of matter on the earth. It is fortunate for us that our atmosphere absorbs most of this ultraviolet or invisible light of the sun, a kind of light which will be explained presently. It has been suggested that, if we received the full flood of it from the sun, our metals would disintegrate under its influence, and this steel civilization of ours would be impossible. But here we are anticipating. We are going beyond radium to the wonderful discoveries which were made by the chemists and physicists of the world who concentrated upon it. The work of Professor and Madame Curie was merely the final clue to guide the great search. How it was followed up, how we penetrated into the very heart of the minute atom and discovered new and portentous mines of energy, and how we were able to understand not only matter, but electricity and light, will be told in the next chapter. The discovery of the electron, and how it affected a revolution in ideas. What the discovery of radium implied was only gradually released. Radium captivated the imagination of the world. It was a boon to medicine, but to the man of science it was at first a most puzzling and most attractive phenomenon. It was felt that some great secret of nature was dimly unveiled in its wonderful manifestations, and there now concentrated upon it as gifted a body of men, conspicuous amongst them Sir J. Thomson, Sir Ernest Rutherford, Sir W. Ramsay, and Professor Soddy, as any age could boast, with an apparatus of research as far beyond that of any other age as the Aquitania is beyond a Roman galley. Within 5 years the secret was fairly mastered. Not only were all kinds of matter reduced to a common basis, but the forces of the universe were brought into a unity and understood as they had never been understood before. 5. The discovery of the electron. Physicists did not take long to discover that the radiation from radium was very like the radiation in a Crookes tube. It was quickly recognized, moreover, that both in the tube and in radium, and other metals, the atoms of matter were somehow breaking down. However, the first step was to recognize that there were 3 distinct and different rays that were given off by such metals as radium and uranium. Sir Ernest Rutherford christened them, after the first 3 letters of the Greek alphabet, the alpha, the beta, and gamma rays. We are concerned chiefly with the second group, and purpose here to deal with that group only. Footnote: the alpha rays were presently recognized as atoms of helium gas shot out at a rate of 12,000 miles a second. The gamma rays are waves, like the X-rays, not material particles. They appear to be a type of X-rays. They possess the remarkable power of penetrating opaque substances. They will pass through a foot of solid iron, for example. The beta rays, as they were first called, have proved to be one of the most interesting discoveries that science ever made. They proved what Crookes had surmised about the radiations he discovered in his vacuum tube. But it was not a fourth state of matter that had been found, but a new property of matter, a property common to all atoms of matter. The beta rays were later christened electrons. They are particles of disembodied electricity, here spontaneously liberated from the atoms of matter. Only when the electron was isolated from the atom was it recognized for the first time as a separate entity. Electrons, therefore, are a constituent of the atoms of matter, and we have discovered that they can be released from the atom by a variety of agencies. Electrons are to be found everywhere, forming part of every atom. An electron, Sir William Bragg says, can only maintain a separate existence if it is traveling at an immense rate, from 1/300th of the velocity of light upwards, that is to say, at least 600 miles a second or thereabouts. Otherwise the electron sticks to the first atom it meets. These amazing particles may travel with the enormous velocity of from 10,000 to more than 100,000 miles a second. It was first learned that they are of an electrical nature, because they are bent out of their normal path if a magnet is brought near them. And this fact led to a further discovery, to one of those sensational estimates which the general public is apt to believe to be founded on the most abstruse speculations. The physicist set up a little chemical screen for the beta rays to hit, and he so arranged his tube that only a narrow sheaf of the rays poured onto the screen. He then drew this sheaf of rays out of its course with a magnet, and he accurately measured the shift of the luminous spot on the screen where the rays impinged on it. But when he knows the exact intensity of his magnetic field, which he can control as he likes, and the amount of deviation it causes, and the mass of the moving particles, he can tell the speed of the moving particles which he thus diverts. These particles were being hurled out of the atoms of radium, or from the negative pole in a vacuum tube, at a speed which, in good conditions, reached nearly the velocity of light, that is, nearly 186,000 miles a second. Their speed has, of course, been confirmed by numbers of experiments, and another series of experiments enabled physicists to determine the size of the particles. Only one of these need be described, to give the reader an idea of how men of science arrived at their more startling results. Fog, as most people know, is thick in our great cities because the water vapor gathers on the particles of dust and smoke that are in the atmosphere. This fact was used as the basis of some beautiful experiments. Artificial fogs were created in little glass tubes by introducing dust in various proportions for supersaturated vapor to gather on. In the end, it was possible to cause tiny drops of rain, each with a particle of dust at its core, to fall upon a silver mirror and be counted. It was a method of counting the quite invisible particles of dust in the tube, and the method was now successfully applied to the new rays. Yet another method was to direct a slender stream of the particles upon a chemical screen. The screen glowed under the cannonade of particles, and a powerful lens resolved the glow into distinct sparks, which could be counted. In short, a series of the most remarkable and beautiful experiments, checked in all the great laboratories of the world, settled the nature of these so-called rays. They were streams of particles more than 1,000 times smaller than the smallest known atom. The mass of each particle is, according to the latest and finest measurements, 1/1,845th of that of an atom of hydrogen. The physicist has not been able to find any character except electricity in them, and the name electrons has been generally adopted. The key to many mysteries. The electron is an atom of disembodied electricity. It occupies an exceedingly small volume, and its mass is entirely electrical. These electrons are the key to half the mysteries of matter. Electrons in rapid motion, as we shall see, explain what we mean by an electric current, not so long ago regarded as one of the most mysterious manifestations in nature. What a wonder, then, we have here, says Professor R.K. Duncan. An innocent-looking little pinch of salt, and yet possessed of special properties utterly beyond even the fanciful imaginings of men of past time. For nowhere do we find in the records of thought even the hint of the possibility of things which we now regard as established fact. This pinch of salt projects from its surface bodies, that is, electrons, possessing the inconceivable velocity of over 100,000 miles a second, a velocity sufficient to carry them, if unimpeded, 5 times around the earth in a second, and possessing with this velocity masses 1,000 times smaller than the smallest atom known to science. Furthermore, they are charged with negative electricity. They pass straight through bodies considered opaque with a sublime indifference to the properties of the body, with the exception of its mere density. They cause bodies which they strike to shine out in the dark. They affect a photographic plate. They render the air a conductor of electricity. They cause clouds and moist air. They cause chemical action and have a peculiar physiological action. Who today shall predict the ultimate service to humanity of the beta rays from radium? End of section 13.